Good evening, everyone. Welcome to the week 12 live interaction session for the course Polymer Concepts, Properties, Uses, and Sustainability. So, as usual, let's just wait for a few minutes for others to join before we begin our session for today. So, I think we can start our session for today. Let me share my screen. Yeah. I hope my presentation is visible and I'm audible. Can anyone confirm quick? Okay, so yeah, that's fine. Thank you. So I welcome you all to the week 12 live interaction session for the course Polymers Concept Properties Uses and Sustainability. This course is offered by Professor Abhijit Deshpande sir from the Department of Chemical Engineering IIT Madras under the NPTEL program. Myself Pratyumnan, a PhD research scholar from the Department of Chemical Engineering IIT Guwahati, Assam. I am responsible for conducting the live interaction session for this course for this particular semester, July to November 2025. So far we have traveled around 11 weeks and we have learned a lot of concepts and a lot about and a lot in general about the polymers, their properties and the uses, and we have also talked about the sustainability aspects of polymers. So if you remember, in the last live interaction session we discussed more on the rheological properties of the polymers. So we first focused our attention towards understanding the fundamentals of rheology of fluids as such. Then we discussed about the non-Newtonian and the Newtonian concepts. We then introduced polymers as a non-Newtonian fluid, and then from that we discussed about different types of non-Newtonian fluids like pseudoplastic, dilatant fluids and Bingham plastics. So after that we discussed about the specific models, specific viscosity models. So we discussed about two major models. One was the linear viscoelastic model and another one is the non-linear viscoelastic model. So in the specific viscous models we discussed about the very first model that we discussed was the Carrio Yasuda model. So there we saw about multiple parameters. So I hope you guys can recollect, or let's go back to that presentation. So if you just a second. So if you remember this equation, we discussed about the different parameters or different variables in this equation. What is eta, what is eta infinity, what is eta naught, their significance, what is lambda, what is a, what is n. So I hope you guys can recollect. So we discussed about what is called zero shear viscosity, what is infinite shear viscosity, and the time constant. What is the significance of the time constant? And based on this model, we introduced the constraint to this model by stating that eta infinity equal to 0. We reduce this model to a simpler form, which is eta equals eta naught times 1 plus um, lambda times strain rate to the whole power a times n minus 1 by a. So this becomes a 3 parameter model. Here we have imposed a constraint. That constraint is that the infinite shear viscosity or the high shear viscosity should be equal to 0. But under what condition would that become 0? So that was a question that we left, or that I wanted you guys to come up with. Under what condition does the value of n infinity becomes equal to 0? Something that is specific towards what we in relation to polymers. Anyone? Under what condition does the value of infinite shear viscosity becomes 0? So the infinite shear viscosity becomes 0 for a polymer melt without any solvents. So in case if the polymer melt that you have do not have or do not use any kind of solvent, then in those cases the infinite shear viscosity will be equal to 0. So these are the two models that we discussed. Apart from that, we also discussed about the other model called Herschel bulk key model. So this model is used to describe the rheological behavior of the polymers. However, they contain fillers which gives them the network structure. So once you add fillers to the polymers, so that typically forms cross-linked networks, and that cross-linked networks affects the rheological behavior. So there we discussed about yield stress fluids and their how does the networked polymer containing fillers behave up to the yield stress and after that yield stress. So they typically exhibit the phenomenon of yield stress where they do not flow until the stress that is applied on them exceeds the yield stress. So once that stress exceeds the yield stress, then there will be a constant flow uh, of the polymer. So this is the concept of Hershey bulky model. And apart from that, there are also other non-linear viscoelastic models such as Fante and Tanner models, which is used to describe the material behavior under large deformation in non-linear conditions. So these models are used for the polymer processing operations more widely. So this is what we discussed about the rheological models. After that, we looked at the swelling of polymers. So under what conditions do the polymers swell? We discussed about what is the swelling phenomena, and in that swelling we have discussed about two concepts of plasticization and solubilization. So we discussed the difference between plasticization and solubilization, and how in case of the cross-linked polymers, specifically the rubber and the thermosets, the swelling usually takes place. After that, we discussed about how, if a polymer can absorb some sort of a solvent and swell, then how much solvent can the polymer accommodate? Is there any factors which affect the quantity of the solvent moving into the polymer matrix? So there we discussed about two types of forces. One was the osmotic force, which is responsible for the solvent molecules to enter into the polymer or its matrix. Then we also discussed about its opposing force, which is the chain elasticity. So what happens is, as there is an influx of the solvent molecules, they tend to occupy the space between the polymer chains, due to which there is a stretching of the polymer. An internal stress actually gets created within the polymer matrix, and this results in the chain to be fully stretched. So that reduces the conformational disorderness as well as the conformational entropy. So the these two factors usually affect how much amount of solvent can actually enter inside a polymer. Then we discussed about what are the factors that affects the swelling. So cross-linking is obviously the very first thing that comes to our mind, whether it has high density cross-linking or low density cross-linking. So as we saw in the last live interaction session, that swelling and cross-linking are have an inverse relationship with each other. So lower the degree of cross-linking, higher will be the swelling, whereas higher the degree of cross-linking, the swelling will be low. And we correlated this observation to what we discussed about the chain elasticity. So more the number of crosslinks, so it will be the chains between the crosslinks, the polymer chain between the crosslinks will be shorter, and they resist stretching more uh, quickly. So because of that, the amount of solvent that enters into the polymer matrix will be less. Then the second factor that we discussed was the polymer solvent interaction parameter. So this has a direct relationship. So better the polymer solvent interaction, more will be the degree of swelling. Then Apart from these factors, we just had a quick overview on what kind of in which places does this swelling is beneficial. So many hydrogel development, wearable electronics and wearable energy storage devices, and in actuators, so in and sensors, all these places, or more often speaking, in places where the polymers actually interface with the human body, in those cases this swelling of the polymer is beneficial. Again, just because the swelling of the polymer is beneficial, it does not mean that high swelling ratio is often advantageous for a particular application. So there is again a trade-off. In some applications you don't actually want your polymer to swell, because that will affect the performance of the application what you're intending to. So again, this swelling concept has its own merits as well as demerits, and this typically depends on, and whether it is advantageous or disadvantageous is going to depend upon what kind of target applications you are actually looking for. So this is what we discussed with until last class. So in today's live interaction session, we shift our focus completely towards understanding how the polymer interacts with our environment. So this we saw previously as well. However, we were not able to give too much concentration on these topics. So in the today's live interaction session, our main aim or focus will be to understand about the polymers and the environment. So that's how the first lecture of this particular week starts with microplastic research. Again, this we have discussed in the course as well as even in the live interaction session in the earlier classes, that microplastics is growing to be a very big concern. The major reason is basically because plastics are not that easily degradable, biodegradable. So they tend to remain in the environment for a very long period of time. So due to this, they can accumulate in the land, soil, or contaminate in the water bodies, and that typically creates an impact on the human health as well as the environment in which we live in. So the major reason why uh, microplastics are becoming a great concern is because of the human is because of human beings, because of the plastic waste that we dump in the environment. This particular problem is becoming a concern in the recent days. So if you see the microplastics, that term, it was coined very recently, just almost only 10 years before this term was coined. So the active concern about the microplastics is growing ever since starting from 2014. So there are a lot of things that has to be done to understand how does this microplastic uh, create an impact, a harmful impact on the environment. So one of the major reasons of this microplastic ending up in water bodies or remain being in the water bodies is because of their low density. So majority of the everyday polymers that we use like PET, polyethylene, all these plastics usually have a density very closer or even lesser than water. So since their density is low, they tend to float in the water. So since they tend to float in the water, they can be easily carried out for longer distance. And since they survive in the environment for a long period of time, they remain in the water bodies for a very long period. And they also tend to get carried away. So the major problems that happens in this microplastic ending up in water bodies is, or what we actually don't know is, if these plastics are going to remain large or big enough for our human eye, then it will not be of a big concern, because we can actually remove these plastics and then we can um, we can use the water. But the problem is, these plastics are going to degrade. The degradation is going to be very very slow, but it is actually going to degrade as the time progresses. Since they remain for a very long period of time, and the degradation is very slow and they remain for a very long period of time, so smaller chunks of the plastics can keep on getting into the water, and that may not be visible for the naked eye. So the main question that comes here is, how does this micro plastic products that we dump in any ocean or water bodies actually degrade? How the breakdown actually happens? Because there is still not much clarity on how the ocean currents or waves or tides actually affects this plastic breakdown, or affects the breakdown in the plastic. Like, whether, so if you see in oceans, we have both hot water as well as cold water streams. So how do they affect the, or how differently do they affect this plastic degradation, is still, there is not much clarity. It's still research question, because there are groups which are trying to understand this particular phenomena of, if you, let's say, take a bottle and you're going to throw it away in the ocean, is it possible for them to track on how this plastic bottle is going to degrade as over the time? How does the currents usually, or the waves and the tides, affect this microplastic breakdown or the plastic degradation? So still there is a lot of room for research in this particular direction on understanding how does the plastic degrades in the water, but still we do not have much clarity on this particular aspect. So, as I said, if the microplastic is going to be, if the plastic is going to be large enough, it is going to be easy. But what happens if they are going to be very small, that it is not visible for our naked eye? So, there comes up the concept of sizes of the microplastics. So, let me just move to that screen. Sizes of microplastic. So the you can say, so the first one, you can say, is the plastics. So the very first one is going to be macroplastic. So macroplastics are nothing but the larger plastic products or objects, so which have a dimension greater than the centimeter, and it can actually go beyond to even having a dimension in the order of meters. So something like your plastic water bottles, or some sort of plastic sheets that we use, um, or some pipes. So those all come under the classification of macroplastics. So large plastic objects, just a second. Large plastic objects, dimension typically varies between centimeters and centimeter to a meter. The second type is nothing but it's called mesoplastic. So mesoplastics are nothing but the fragment of the larger plastic products. They typically have dimensions within the centimeter range, but again smaller than the microplastics that you actually see. And this fragmentation usually happens because of erosion, aging, some sort of embrittlement, or the mechanical and the thermal fluctuations that usually that the polymer is subjected to. Due to that, they tend to degrade, or you can say they tend to break down. Fragments of polymer of the plastic is formed, and those are actually termed as mesoplastics. Then comes the microplastics. So they are actually even smaller than the mesoplastics, which have a size typically in the order of micrometers. So usually something that is in the order of 1 to 5 micrometers, or we even classify sizes smaller than 1 micrometer also in the as microplastics. So they are more smaller. So the size typically is less than 1 millimeter. So they are called as microplastics. So usually the source of origin for the microplastic is two. One is the primary and the other one is the secondary source. So any idea on what are the primary and the secondary sources? Two sources of origin. Primary source, secondary source. So what are the two sources, and like what is the difference between the primary source and the secondary source? Anyone? What is the primary difference between the sources of origin, that is your primary and secondary? Okay, so please look at the different types of origin. So as I have told right now that the microplastics are usually smaller. They have a size almost less than 1 millimeter. So their sizes typically range in the order of micrometers, or you can even say in the order of 100 to 100 nanometers to 1 micrometer, which is very difficult, I mean, which is impossible for a naked eye to actually um, naked eye to identify the plastic in the medium. So because of that, that basically becomes a main problem, and due to which the microplastic contamination has become wider and wider. So there are several reports which states that almost in every region of the planet, starting from the ice glaciers till the deserted areas, and I mean almost everywhere in all the water bodies, there are a lot of evidences of microplastic contamination, including the human body as well. So majority, or you can say the most common microplastics are from the polymers, are from these polymers. So the first one is I mean, I'm writing this in no order, so do not assume that PVC is more in concentration. So this distribution of the microplastics vary widely depending upon the geographical condition, the type of plastics being used by the people in that particular geographical area, in that geographical location. So it will vary significantly. So PVC is one common with polymer that is found. Polypropylene, polystyrene, polyethylene terephthalate. So this is predominantly the most common microplastic found in many areas, including water bodies, land, and soil, etc. And sometimes polyethylene as well as polymethyl methacrylate. So these are the common examples of microplastics. Now the question is, so we do know that microplastic is there in the water bodies. Let's talk first, keep our discussion to water bodies. We know that microplastic are present in water bodies as well as in other what do you say, as well as in other places as well, land and soil. But then why we are unable to remove them or separate them so that the water that we get is free of microplastics? What could be the typical reason why, even though we know that microplastic exists, we do not have a developed technology to identify what kind of microplastic is present, or more than stating that, how much, what is the concentration of the microplastic that is present in, let's say, a lake, or that is present in the lake, and why we are not able to separate those microplastics so that we can get fresh water for our daily purposes. And even though it is mentioned that this particular location has these microplastics, those are there any evidences of what is the concentration of the microplastics that is present, or that type of microplastic that is present in that particular ocean? So why we are unable to find a solution so that we can separate these microplastics from our water bodies or land or soil. What is it that is creating a challenge in this, in doing it? So any I guesses on what could be the reason of why microplastic challenge is really is quite a task actually solve to solve the problem. So, for example, if it is arsenic, we know how to remove them. If there are some other dye contaminants, we have technology to remove. For salts, if there are if we if the water has salt, we know how to remove the salt so that we can get fresh water. Like that, why don't we have a technology that is developed for microplastics? Or what is the difficulty in developing such technology? Or quantifying how much microplastics is present in a particular location or in a given sample of water? Any idea on that, or guesses on what could be the reason? So it is predominantly because of the fact that they do not exist in uniform shapes. So they have a shape, they have a wide variety, they exist in wide variety of shape and they're smaller. So that's what makes it difficult, and moreover the nature in which they exist. So it's not going to be typically just one type of plastics that is going to be present. There are n number of plastic contaminants that are going to be present, so that makes it difficult to understand on how we can go for developing such technologies. And since we are in the early stages of the microplastic research, so that is also one of the reasons that is contributing. But the major problems with this is the fact that the shape and the form of the microplastics that are there are varied. So shape, size, and the nature of you can say microplastics is diverse, and this creates a lot of difficulties in quantifying the concentration in a given sample and their removal methods. So this is the main issue with the microplastics as such. So their small size is what something that is providing them the advantage, because since the size of the polymer is going to be small or the microplastics is small, the surface area to volume ratio is going to be greater, and because of which the interaction of the microplastic with the surrounding environment is going to be more. So there is an enhanced interaction with the surrounding, and the enlarged surface area makes adsorption, leaching, and degradation more effective. So due to this, the small microplastics that are present, they change the surrounding medium, and this can affect the aquatic life if present in water bodies, because they can affect the concentration of the dissolved oxygen that is present in the water bodies, so making aquatic life difficult. Also, if ingested, they can lead to biomagnification and accumulation within the animal as well as that of the human body, and this could also lead to health impact. So this is about the microplastics as such. So the major reason is because polymers tend to stay in the environment for a very long time. So now we move towards the concept of biodegradable polymers. So the polymers that tend to degrade at a pace faster compared to the non-degradable polymers. So the major polymer degradation typically happens usually because of air, water, UV radiations, or it can happen in soil. So radiation exposure is one of the ways of polymer degradation. So the UV radiation causes for this degradation. So either in the form of cross-linking or hydrolysis or some sort of oxidation. Second way for the degradation in the polymers is through thermal and mechanical ways. So the temperature fluctuations that happen within the environment, and if the polymer is going to be subjected to mechanical loads, so there can be abrasion and the erosion within the polymers, which can lead to their degradation. And if the polymer, other than being subjected to UV radiation or moisture, if they are subjected to very high temperature and pressure, just like how petroleum is obtained from biomass, like that this polymers can also can also undergo some sort of a chemical transformation to form other products or other components. The last one is the biodegradation. So there what is typically employed is some sort of an enzyme which tends to break the chemical bonds in the polymer and lead to their fragmentation or degradation, as we can say. So in this biodegradation case, what happens is there are certain bacteria, or you can say microorganism, which uses polymer as a food source and break down these polymer macromolecules into smaller fragments. So one of these ways that it does this is enzyme involvement. So using enzymes that this microorganism secretes, they break this chemical bond or the chemical bond in the polymer macromolecule and convert it into smaller fragments, and then digest it and excrete it out into some safer products or mm, safer byproducts or waste. So recently there has been recently a group of researchers have found a particular fungi which feeds on polymers and can generate, it actually breaks down this polymer, and then after that it excretes out waste products which does not cause any harm. So any idea on that? I think this I said in previous live interaction sessions also. Has anyone looked at what is the fungi, or what fungi am I talking about? Anyone? So please have a look at it. What fungi is this? So it will be interesting to read. So one is through enzyme involvement, where the enzyme actually breaks the polymer, convert it into smaller fragments, and then use that as a and then it gets used. The other thing is where the microorganism cannot actually feed on that polymer, because since polymer is going to be a very large macromolecules, there may be microorganisms which cannot actually feed on the polymer directly but can actually feed on the smaller fragments of that polymer. So in that case what actually happens is, first the chain is actually broken down. Either this can happen through hydrolysis or oxidation, and then they are fed, the microorganisms are fed on this broken chain so that they can use that polymers as a food source, can be used as a food source. So this is one way. Usually after this polymer is I mean, after this digestion of the polymers, the end products are usually either carbon dioxide or water, and some other inorganic substances with water is also possible. But the major thing that we have to keep here in mind is that the rate of biodegradation, so the pace at which this organisms feed should be greater than the rate of accumulation of the waste in the environment. And then the second is that the intermediate products that are generated during this process should be non-toxic. In case of biodegradation, two things has to be kept in mind. The first one is rate of biodegradation, and then the second one is, oh sorry, the rate of biodegradation, let me write it completely, should be greater than the rate of accumulation of plastic waste in the environment. And the second thing is the intermediate product that are generated should in the process should be non-toxic in nature. So these are the two conditions that has to be made. So one is that the rate of biodegradation should be greater than the rate of accumulation. Another thing is that the intermediate product that gets generated in this process should be non-toxic. Again, various factors usually affects this biodegradation. One is the water, pH, oxygen availability, nutrients, disposal context. There are so many factors which affects this degradation of polymers, or you can say the plastics as such. So there are many naturally occurring, and there are many synthetically available biodegradable polymer as well. So if you can give any example of naturally available biodegradable polymer, anyone? So you have starch, chitin. Then you can also tell PHB, polyhydroxy butyrate. So these are some of the examples of naturally available. In case of synthetically available, you have polylactic acid, and in polyesters you have examples like polybutylene succinate, polybutylene adipate terephthalate. So these are some of the polyesters and the polyesters as well as polylactic acid that are available, that are synthetically available. In case of naturally available, you have starch, chitin, PHB, and etc. So we come to an end of our discussion here. So we have some problems to solve. In case if you have anything to ask, you are welcome to ask me now. Or else, so let's take a break for around 5 minutes, and then let us come back after some time. So So I hope you would have found out the answer for these three questions. So before that, if you have any doubts, you are welcome to ask me, or otherwise we can start answering the questions one by one. So let's start with the first question. I hope there are no doubts in what we have discussed so far. So the first question is PHA depolymerases helps in the biodegradation of which of the following biodegradable polymer? Is it starch, or is it polyhydroxybutyrate, or is it cellulose, or is it polybutylene adipate terephthalate? Yes. What is PHA? What does PHA depolymerization? Polymerization is something where you try to break the polymer chain. So it's like an enzyme which is used to break the polymer. But what is PHA? What is the full form of PHA? It is PHA is polyhydroxyalkanoate. This is fine. PHA depolymerase. Now you need to tell for which one does this PHA polymerases is used. It is is it polyhydroxybutyrate or polybutylene adipate terephthalate? It is polyhydroxybutyrate. So that is the polymer, I mean PHA depolymerases is used for the degradation of polyhydroxybutyrate. So have this in mind. Next, identify whether the statement is true or false. Starch can be processed as a thermoplastic by using sorbitol as a plasticizer. True or false? Starch, whether can it be used as a thermoplastic upon using sorbitol as a plasticizer? So, question is, if sorbitol is used as a plasticizer and then starch is processed like a thermoplastic, so starch indeed, I mean, starch alone is a thermoplastic or a thermosetting plastic? Anyone? Whether starch without adding any other plasticizer or as such any other additive, is starch thermoplastic or thermosetting? So starch, if you see the native starch, actually it is not a thermoplastic. But if you want to use this as a thermoplastic to process for some shapes or for some material, then you need to use a plasticizer, and sorbitol is one of the plasticizer. So this is true. So next question, Identify if the statement is true or false. Vegetable oil are explored as an alternative for the synthesis of thermoset polymers such as epoxy resins, polyurethanes due to the presence of multiple unsaturation triglycerides that constitute polymerizable groups or moieties. So whether that is true, whether can you use vegetable oils for the synthesis of thermoset polymers? If yes, is it basically because of the fact that there are multiple unsaturated triglycerides that is present which provide this polymerization ability or moieties for polymerization? So it is true because this unsaturated triglycerides actually have polymerizable moieties. So once that polymerization happens, they actually form thermoset polymers such as epoxy resins and polyurethanes. So let's go to next question. Question number 4. Toxicity intermediates are acceptable in biodegradation. This we just discussed right now. We discussed about the two important things that we need to actually keep in mind during this biodegradation process. One is that the rate of biodegradation should be greater than the rate of accumulation, so that it's not that lot of accumulation happens. Then there is a next thing about the toxicity of the intermediates. Whether is it acceptable for the intermediate to be toxic or should it be non-toxic? We discussed this just right now. So it is true, right? It is false, right? You cannot have toxic intermediate. So that is what is the condition. The intermediate products that are generated in this process should be non-toxic in nature. So if they are going to be toxic, then that is again going to cause a harm to the environment. So false. Toxicity intermediates are not acceptable in biodegradation processes. So let's move on to question 5. Pick the correct sources for different size of plastics in the environment. You have four options. Who knows what is that correct sources for different size of plastics in the environment? So first of all, what are the primary and the secondary sources? Because so let's leave this question for the time being, because since no answers on what are primary and secondary sources of plastics in the environment, so let this be there. Now, next question is, arrange the degradation steps of polylactic acid in the presence of water. It's not MCQ. You have to arrange the steps of how this. If you put PLA in water, how does the degradation of PLA happens in water? You need to arrange it in arrange the order. So A, B, C, D are given. So you need to tell in what order does the degradation progresses. Yes, anyone on what are the degradation steps of polylactic acid in water? How does the degradation actually progresses? So first thing should be that there should be diffusion of water in PLA. So this is the first step. So C should be first. Now question is whether after that diffusion, whether that hydrolysis that is going to happen, is it going to happen in amorphous domain or is it going to happen in the crystalline domain? Which is more easier for hydrolysis? Is it amorphous or is it crystalline? So obviously it's going to be the amorphous domains, because amorphous domains have more randomness compared to the crystalline domain. In crystalline domain, there is this period ordered arrangement um, of the cells. So whereas in case of the amorphous domain, you do not have that orderedness. There is a randomness more in case of the amorphous domain. So hydrolysis over there will happen first. Then because of this hydrolysis, there will be a decrease in the molar mass of the amorphous domain. Then after this happens, meanwhile there will be a hydrolysis in the crystalline domain as well. So once this happens, the hydrolysis happens in the crystalline domain. Also, because there is this degradation that is happening in the amorphous domain, the acid concentration, lactic acid concentration will also keep increasing, which will again aid in the hydrolysis of the crystalline domain. So the order should be C, D, B and A. So this is the degradation steps of the PLA in the presence of water. Now, let's move on towards a numerical problem. So it's a very simple question. Here you need to calculate the surface area to volume ratio for a spherical particle, and for two different spherical particle, one is basically going to be a plastic ball of radius 5 centimeter, and another one is going to be a tiny microplastic sphere with a radius of 50 micrometers. Now you are supposed to comment, after calculating the surface area to volume ratio, you are supposed to comment which one will have more interaction with the environment and their species in the environment. So calculate the surface area to volume ratio. Based on that value, we can see which one will have increased interactions. I think this should you everyone should be able to calculate this. It's a very simple calculation. So surface is just surface area and volume of a sphere, and the rest is just substituting the values. So what is the surface area of a sphere formula? surface area of a sphere formula, and again volume of a sphere as well. So it is 4 pi r square for surface area of a sphere. 4. So if you 4 pi r, yes, so please solve with me. This will be useful. So 4 pi r square, and volume will be 4 by 3 pi r cube. So now we need to calculate for the first case surface area to volume ratio. Let me give it as S by V. So that is going to be 4 pi r square divided by 4 by 3 pi r cube. So what will it be? 3 by r? Is it fine? So now you know that the relationship is 3 by r. So then for the first case, it's S by V is going to be, just substitute 3 by 5 centimeter, or if you express this in meter then it will be 0.05. That will be that will be 300 by 5, which is 60. Next, the next one will be S by V is 3 by 50 micrometers, so that will be 50 times 10 to the power minus 6. So that will be Is this fine? Hmm. So now you can see which one has a greater surface area to volume ratio, the tiny microplastic sphere. So since the surface area to volume ratio for that microplastic sphere of radius 50 micrometer is greater, so that will have increased the interactions with that of the environmental species. So this is typically a kind of a problem to emphasize the fact that why the microplastic have more harm compared to the microplastics that you see. So because of this high surface area to volume ratio, the chances of interactions or the interactions with the of the microplastic with the environmental species is going to be here is more. Larger surface area means larger space for the absorption, leaching, degradation, and more. So interactions will be enhanced in case of the microplastic sphere, which will be less if you take it for a macroplastic or a plastic ball of radius 5 centimeters. So let me just quickly write this: tiny microplastic sphere of 50 micrometers radius will have increased interaction. So this is for today's session. So in case if you have any doubts, you are welcome to ask me now. Do you have anyone has any doubts? Just a second. So if you have no doubts, then let's conclude the session for today. So let me just stop presenting. Yeah. So if you have any doubts, you are welcome to ask me, or I think we can conclude our session for today. We will be having one more summary live interaction session tomorrow, same 5 p.m. to 7 p.m. So over there we will be discussing on some of the major concepts, like almost we have come for 12 live interaction sessions, so we will be taking up with certain concepts which we were unable to cover during the regular live interaction session. So yeah, so if you have no doubts, I think I can conclude the session for today. So yeah, Thank you everyone for joining today's live interaction session. Our final session will be tomorrow from 5 p.m. to 7 p.m. I thank Professor Abhijit Deshpande sir as well as the NPTEL team for providing me this opportunity to interact with you all on this Sunday afternoon. So my email ID will be available along with the presentation which will be uploaded by next week. So if you have any queries, you are also welcome to email me. So thank you. Have a wonderful weekend and a great week ahead. Thank you and bye.